Hi you guys, today I'm going to talk to you about the periodic trends. Periodic trends are specific patterns that are present in the periodic table that illustrate different aspects of certain elements. Some of the periodic trends that we will talk about today are atomic and ionic radius, ionization energy, electron affinity, and electronegativity. So grab your notes, pencil, pen, highlighters, and your periodic table, and let's get started with the notes. Okay, so the modern periodic table is arranged based on two criteria. The first criteria is increasing atomic number, and that is to say that the modern periodic states that if the elements are arranged by increasing atomic number, the elements will exhibit periodic recurrence of similar physical and chemical properties, which is known as periodicity. The second criteria that's based on the modern periodic table is parallel electron configurations. So one of the reasons why we talk about periodic trends after electron configuration is because you need to truly have a good understanding of electron configuration. That is, know where these electrons are located, because if you understand where these electrons are located, then you understand how they are affecting the force, or how they're influencing the physical and chemical properties of that element. Okay, so electron configuration is the distribution of electrons within the orbits of an atom. Elements are arranged so that elements in the same column have the same number of electrons in their outermost energy level. When we say outermost and energy level, realize, you guys, that we are talking about those valence electrons. Okay, so if we go to your periodic table right here, if you look at your periodic table, now as you move across the periodic table, notice how the atomic number is increasing. And also, if you move down the periodic table, your atomic number is also increasing. So that's the first criteria. The second criteria talks about electron configuration. And what it is saying is that elements that are in each group of the periodic table seem to have the same number of valence electrons. And that's true. They do have the same number of valence electrons, which you learned in your previous lecture covering electron configuration. So if we go back to your notes, let's talk about the factors that affect the periodic trends. There are four factors that affect the periodic trends, and that is distance from the atomic nucleus to the valence electrons, total nuclear charge, the number of energy levels between the nucleus and the valence electrons, and electron repulsion. But before you can even understand that, you really need to understand something called Coulomb's law. So let's write down Coulomb's law. Okay, this is Coulomb's law right here. It is force. This F stands for force, or electrostatic force. Okay? This K is something you really don't have to worry about, but it is a constant, so we don't really have to worry about it. And then it is Q1 times Q2 divided by R squared. Okay, so both Q1 and Q2 happen to be particles, charged particles. Okay, now whenever we think of charged particles, we think of positive and negative electrons. So, and that's exactly what we're thinking about. If Q1 happens to be Q1 and Q2, and so Q1 could be the proton and Q2 could be the electron. They could both be electron-electron or proton-proton. It really does not make a difference. And then the R value is actually the distance between Q1 and Q2. Okay, so really this equation, Coulomb's law, can be divided up into two parts. The first part that we have, Coulomb's law, can be used to describe just force and the charge. Okay, now the second law then can be used to describe the force and the distance right here. Okay, so let's talk about the force and the charge. So if you have force is equal to Q1, Q2. Notice that this is a direct relationship, okay? It is a direct relationship. That is to say, the greater the charge, the greater the force will be. So part 2 of Coulomb's law, and I'll just write part 2. And this is, of course, part 1. Okay. So part 2 of Coulomb's law actually talks about how force is proportional to 1 over r, or the distance between the charged particles. So, and this is what we call an inverse square relationship. So it's inverse square relationship. Okay. So hopefully you know that the word inverse means is that if the force increases, then the distance will decrease. So they're the exact opposites of one another. Okay, so let's figure this out. Let's say that you have a particle, a positive and a negative. So you're comparing a proton, the attraction of the proton and the attraction of the electron to one another. So they're both going to be attracted to each other. So we're going to say force is equal to a positive 1 times a positive 1 times a negative 1, okay? And then we're going to say that these two have a distance of 1, okay? So we're going to say 1 squared. Well, that does really help you understand what Coulomb's law is saying, because really it turns out that the force is just, and this negative sign right here means attracted, that the force, that the particles are attracting one another, attracting of particles. And that usually happens when you have a proton and an electron that are attracting one another. So this actually gives you a 1 value, a negative 1 value to be more exact, and that's fine. That really doesn't illustrate the inverse square of a relationship. But let's do this now. Now you still have 1 proton and 1 electron, but now let's say that the proton and the electron are somewhat away from each other, and we'll say that the R value is 2. So now that they are, the R value is 2. Notice how much that does influence the force. Now this 1/4 actually means that the force is decreased by 4 times. So the force is actually 4 times less than it was. And if we continue the same thing here, plus 1 times minus 1, and let's say the distance between them is just now r is equal to 3. These seem like really small numbers, 2, 1, 2, 3, but when we talk about inverse square, these numbers can really add up. So now we're saying that the force is about 9 times less than it was before. So it is 1/9 of the value, or 9 times less. So that inverse square can definitely influence the amount of force that is between the charged particles. Okay, so let's go back to our notes now. Okay, so let's start on our first factor. The first factor is distance from the atomic nucleus to the valence electron. So the electrons and protons are attracted to each other by opposite charges. We know that to be true. However, the larger the atomic radius, the weaker. And I want you to underline weaker the force of attraction. Okay? The force of attraction is weaker. That is to say that energy level 1 is closest to the nucleus, and each succeeding energy level is further away from the nucleus. So let's look at the periodic table then. And if we look at the periodic table and we look at energy level number 1 and going down. Now notice that energy level number 1, the electrons are pretty close to the nucleus, but as we go further down, the electrons, they move further away from the nucleus. So here's an illustration that actually shows this. Okay, so we've got hydrogen, lithium, and sodium. All three of these elements are right below one another. Each one, this is in period 1, period 2, and period 3. The way that I can actually tell that which periods this is in, notice that hydrogen only has one energy level, so it must be in period 1, and it's got 1s1, the electron configuration for it. Lithium has 2 energy levels, so it must be in energy level number 2, and sodium has 3 energy levels, so it must be in the 3rd energy level. Now notice that that you can clearly tell the size of the atom as you move further down. So hydrogen seems to be tiny compared to how sodium is. But also look at how close this electron is to the nucleus. It's pretty close. But as the atom gets bigger and bigger, that valence electron, and I've highlighted the valence electrons for you, that valence electron gets further and further away from the nucleus. Now let's go back to your notes. And in your notes right here, realize you guys that when we talk about the distance of the protons to the valence electrons, we are actually talking about Coulomb's law. So let's write over here that force is proportional to the distance squared. Okay, and there's that that inverse square relationship again. So the larger the atomic radius, the weaker the force of attraction, and that's the force that we're talking about. So if this increases by 2, then the force will decrease 4 times. Okay, so because we're talking about the energy level going in the periodic table from the top to the bottom, right here on the periodic table, we're talking about going from the top to the bottom. We're talking about actually adding the energy levels. So let's go back to your notes then. And in your notes, write down additive energy levels. Okay? So moving on with your notes, now let's talk about total nuclear charge. First of all, what is that? Well, that's a very simple concept to understand. So if you go back to your periodic table, the nuclear charge that we have, the total nuclear charge, is the number of protons that you have. So as you move across the periodic table, as the atomic number increases, so does your nuclear charge. And as you move down the periodic table, your atomic number increases, so does your nuclear charge. So it's really not a hard concept to understand. Just understand that nuclear charge means the charge of the nucleus, which has the protons in it. Okay, so if we go to the total nuclear charge, the importance of this characteristic is most visible across the periods. Increasing the nuclear charge increases the force of the attraction between the nucleus and the valence electrons. Okay, so let's go back to your periodic table. So I'm going to illustrate the concept of nuclear charge with the elements lithium, beryllium, and boron. So notice they are on the same period of the periodic table. And as you increase the nuclear charge, 3, 4, and 5, you also increase the attractive force that is between the nucleus and the valence electrons. So let me show you how that looks. Okay, now I have lithium, beryllium, and boron. All of them are in period 2, so they have 2 energy levels. But notice that lithium has 3 protons in it, and the nucleus, and so there are 3 protons around, there are 3 electrons for lithium also. Only one of the electrons is a valence electron, So there's pretty much a pull, an attraction between the protons and the electrons right here. As you go to beryllium, beryllium has 4 protons in its nucleus, but now it has 2 more valence electrons. So there is even a stronger pull. The force is now increasing between the nucleus and the valence electrons, only because the number of valence electrons is increasing. So the nucleus is holding tight or even pulling these electrons towards it, inward. And then if you look at boron, it's got 5 protons, but now it has 3 valence electrons in its outer shell. So these 5 protons are now pulling all 3, if not all of these electrons towards it. So it's pulling it even closer. The force is increasing, and as the force is increasing because of the atomic number, those electrons are being pulled even harder. So the force is increasing, so your atom is getting smaller. So let's go back to your notes then. So in this case, we're going to say, so atoms get smaller from left to right on the periodic table. So what this is really talking about is it's talking about the relationship between force and charge. Well, you guys, you know that the relationship between force and charge is actually the first part of Coulomb's law. Q1 times Q2. Remember, as charge increases, the force also increases. Keep in mind that this is a direct relationship, okay? Where this one is an inverse square relationship, okay? So keep that in mind. The fourth one is the number of energy levels between the nucleus and the valence electrons. Now, what we say is that as atoms gain energy levels, the force of attraction acting on the outermost electrons decrease, okay? This is called the shielding effect, okay? Which means having several layers of electron orbitals between the nucleus and the valence electrons decreases the effective force felt by the valence electrons, okay? So this is shielding. Go ahead and write shielding here again, which is exactly what the word shield means. Shield means to protect, or it's to protect or prevent something from happening. Okay, so going back to this illustration right here, so you've got lithium here, 3 protons, and you've got this 1 electron right here. Well, these electrons are attracted, they're being pulled to the nucleus. What's interesting is that these electrons here are also repelling one another. So they're actually shielding the nucleus, from the valence electron. It's not happening so much with lithium here because there aren't that many electrons. But so if we look over here for beryllium. Now for beryllium, you've got 2 valence electrons right here. These 2 valence electrons are not only being attracted to the nucleus, but they're also repelling from the other electrons right here. And that's what we call shielding. The shielding means is that these electrons are actually getting in way of the valence electrons, because every electron is being pulled to the nucleus, not just the valence electrons. So the electrons that are closer, they're going to be pulled further, and they're going to tell the other electrons, no, get away. They're going to repel one another. And that's exactly what's happening with boron also. So as you move down the period or move across the period, the shielding effect increases. If that doesn't make sense to you, then just look at this where I have sodium right here. Now the valence electron that I have for sodium is right here. But look at sodium. The valence electron's right here. It's got 11 protons, but all of these other electrons are also being pulled towards the nucleus. So, and this 1 valence electron, well, it's repelling. It not only is being pulled towards the nucleus, but these electrons right here are all repelling against the nucleus, only because they have negative charges, and negative repel one another. So that is a form of shielding that is going on for these elements. And of course, when we talk about the shielding effect, we can't help but talk about the electron-electron repulsion that is going on, where electrons have the same charge. And so if they have the same charge, they're going to end up repelling one another. So in order to accommodate this, what they're trying to do is that these electrons will need to, they need more space. More space. Okay, they need more space, so they're going to try to adjust with one another. They're going to try to adjust with one another by moving around a little bit. Okay, so now that I've talked to you about the factors that affect the periodic trends, let's actually talk about the periodic trends. The first periodic trend that I'm going to talk to you about is the atomic and ionic radius. So the atomic size is actually, we are talking about the neutral atom electron cloud. And when we measure it, we are actually measuring from the center of the nucleus to the outer edge of the electron cloud. So let's look at the families or the groups on the periodic table and how the atomic radii increases as you're going down the column. So here, you guys, I have my periodic table as well as my illustration. As I am moving down the column, my atomic radii increases. Okay, and that is to say, you can actually look at it and notice that as I'm moving down the column, my number of energy levels increase. Because my number of energy level increases, the distance between the nucleus and the valence electron also increases. It may not be so apparent for the hydrogen, but by the time you get to the sodium, you can see that there is a big difference in the number in the force between the nucleus and the valence electron. Keep in mind that we are talking about Coulomb's law for the first one, where we're talking about the distance between the nucleus and the valence electron right here. Okay, so if we go back to your notes right here, our reason would be the atomic radius increases going down. We would say it is due to number one, or the very first factor in our notes, which states the distance from the atomic nucleus to the valence electron. It is increasing because our energy levels are also increasing. Okay, now let's look at how the period affects the atomic and ionic radius of an element. So the atomic radii decrease moving across a row. So looking at your periodic table in this illustration right here, if you look at this as you're moving across the period, notice that the elements lithium, beryllium, and boron. Lithium, the nuclear charge is also increasing. So if the nuclear charge for each one of these elements is increasing as you move across the periodic table, so is the force between the nucleus and the valence electrons. So what's happening is eventually this nuclear charge is pulling everything together, and that is the effect of the total charge. So going back to your notes, we would say why? That is because of number two. Number two is the reason why, where the total charge is influencing the radius. The higher the charge, remember, the greater the force. And so in this case, as we're moving across, we have a higher charge. And more valence electrons are coming about, so we have a greater force that is pulling that nucleus together. Okay, so the atomic nucleus is actually decreasing because that force is pulling those electrons, or the protons are pulling the electrons closer to the nucleus, making the atom smaller. Okay, so this illustration actually shows how the atomic radius is influenced on the periodic table. As you move down the group on the periodic table, notice that the radius of the element increases. But as you move across the periods, notice how the atomic radius of the element is now decreasing as you move across. Okay, so moving on, let's talk about ionic size. And that itself, you guys, ionic size is actually the size or the radius of the ions, and that is a little bit more complicated to talk about. Okay, so when we talk about the negative ions, usually we're talking about the nonmetals, and these nonmetals are the ones that end up gaining electrons. So they are usually larger than the neutral atom that they form from. And because they're gaining electrons now, you're going to see a lot of electron to electron repulsion, which is factor number 4 that affects your periodic trends. The positive ion, on the other hand, is usually the metal, which is right here, and they're usually smaller than the neutral atom that they form from, and that's because those elements right here are the ones that are losing electrons. So the nuclear charge is pulling on those electrons, but those electrons have already left because they've been lost. So your ion is going to be smaller than your neutral atom. So that is actually number 2 for when we are talking about the nuclear charge. Okay, so now let's talk about ionization energy. Ionization energy is the energy required to remove the outermost electrons from an atom. And we can look at the ionization energy looking at the groups and the periods on the periodic table. So if we're looking at the groups or the families on the periodic table, the trend for ionization energy tends to decrease as you're going down the column. Okay, and let's look at your periodic table. Okay, so as we look down the group, notice how the atom keeps getting bigger and bigger as you move down the group. And as your atom gets bigger, there are more electrons that are in the way. Because these electrons are in the way, all these electrons are being attracted to the nucleus, which is made up of protons. So this valence electron has a whole bunch of other electrons that are shielding it from the nucleus. Okay, so because that electron is being shielded, there's going to be less force that's going to cause this valence electron to stick around, and so it's going to be a lot easier to get rid of this valence electron. So as you move down, the atom gets bigger in size. If it does, there's more shielding that gets in the way, allowing the valence electrons to be released easily. So if we go back to your notes, ionization energy tends to decrease going down the column, and that is completely due to shielding, which is number 3 on the factors that influence periodic trends. So let's talk about the period. On the other hand, the ionization energy tends to increase as you're moving across the row. So let's go back to your illustration and your periodic table. So if we go back to this illustration right here, looking at this illustration, notice how your nuclear charge is increasing as you're going across the periodic table. And because your nuclear charge is increasing, the force that's between the nucleus and the valence electron is also increasing. Okay, so for that reason, we're going to have ionization energy is going to increase, because now it's going to take more energy to remove these electrons, these valence electrons, which the nucleus is holding on to. Keep in mind, you guys, that is Coulomb's law, whereas the greater the charge, the greater the force. Okay? So if we go back to your notes, ionization energy tends to increase moving across the row because of number 2. The greater the charge, the greater the force of the atom or the nucleus on those valence electrons. So it's going to be hard to get rid of that valence electron. Okay, now moving on with your notes. Okay, so the ionization energy trend would be as you move across the periodic table, it increases. And keep in mind, you guys, that as you move down the periodic table, your ionization energy decreases. So if you're moving up, then your ionization energy will increase. Okay, so this arrow is the opposite of what I actually explained to you guys, which is moving down the periodic table. Let's talk about multiple ionization energies. Multiple ionization energy. It is possible to remove more than one electron from an atom. Okay, as successively more electrons are removed, it takes more and more energy. This is a very large jump in ionization energy if electrons beyond the valence electron are removed. Okay, so, and that is very true, that it's a very large jump. So underline that, circle that. So if we look at this, let's look at magnesium right here. Okay, circle that because that's what we're going to be looking at. So you have magnesium, and the very first electron in magnesium is okay to move. It takes about 736 kilojoules to remove. Then when you go to magnesium and you remove the second electron, it takes about twice as much energy, but it's still doable. You can remove that second valence electron. Keep in mind, you guys, that magnesium can have up to two electrons that can be removed. So we can say that 736 kilojoules, okay, is about twice as much, 2x to 1445, okay, kilojoules. So let's talk about this. Magnesium ion, when we remove that one electron, the electron configuration will look a lot like sodium neutral atoms configuration. When we take away the second electron from magnesium, or now we have Magnesium Two Plus Ion, well, this ion looks a lot like the electron configuration of neon. But, and this is where it makes a really big difference, when we remove that third electron, so if we have Magnesium 3 plus, that third electron now is going to, the electron configuration for that is going to look a lot like the electron configuration for fluorine. And that's a big problem, because if you look at the periodic table, here's magnesium. It looks like sodium if you take that one electron out. Then it looks like neon if you take that second electron out. But if you take that third electron out, now we're talking about fluorine right here. That's a big noble gas jump. So this is broken. That noble gas configuration has broken a noble gas configuration. Because remember, the noble gas configuration for magnesium is really neon. And after neon, if it goes further than that, then it's breaking that noble gas configuration of neon that is a very stable element. Okay? So this is a very huge, and we say huge jump. Okay? To 730 kilojoules. Okay? That's a huge jump. So that's what would happen if it was going to fluorine. Okay, so let's talk about electron affinity. Electron affinity is the energy released when an atom gains an electron. It's the tendency of an atom to gain any additional electrons. Well, that's going to be really hard for metals, because metals usually don't gain electrons. They're the ones that lose the electrons. So they will have a tendency to have low electron affinities, because they're able to have they are able to lower their overall energy by losing electrons rather than gaining them. And that's why metals usually form the positive ions. Your non-metal ones are the ones that gain electrons, so they have a tendency to have high electron affinities. They lower their energy by gaining electrons, and that's why they form negative ions. Noble gases, on the other hand, remember, noble gases are called inert gases, or they're very stable. And that's because they already have an octet, which means that they have 8 valence electrons in their outer shell. So they actively repel any additional electrons because they just don't have room for it. All their shells are filled, and it's the golden number 8. Electronegativity, on the other hand, is the attraction of an atom for electrons in a chemical bond. So you're now attracting electrons in a chemical bond. Metals will have a low electronegativity. And going back to the illustration, so if we go back to the illustration right here, realize that this sodium is going to have a tendency to lose its valence electron because of shielding. Even though you have the nucleus right here that's pulling on all the electrons are being pulled to the nucleus, so the other electrons will shield this valence electron. So it's going to be very hard for this metal to actually hold on to its valence electron in the outer shell, let alone try to gain another electron, which is what electronegativity is, attraction of electrons. On the other hand, you guys, if we just look at the metals, they follow the same principle as these elements here. And if we look at the periodic table, as you're moving across the periods here, the non-metals will have high electronegativity. That's because the non-metals, as you go down across the period, your nuclear charge is increasing. The nucleus is pulling onto those valence electrons, making the atom smaller and holding tightly onto those electrons. So the nucleus will pull any other electrons that come to it. It will pull those new electrons even closer, holding them more tightly. That's because it wants to form an octet. Okay, so let's go back to your notes. Okay, and we can say that the nonmetals have a high electronegativity. That's because the nonmetals hold their outermost electrons tightly. They're trying to pull those electrons closer because of the octet. And this, you guys, circle it. This is a really big deal because that's what they're trying to meet. So I guess you can write bingo. Okay, because that's what they're trying to get. Your noble gases, on the other hand, will have zero electronegativity because they don't need to form any chemical bonds. They meet their octet rule as it is. So going back to the last page of your notes for periodic trends, you have the octet rule. Oh, before we do, let me just go over this chart right here, that electronegativity. So as you move across the period on your periodic table, your electronegativity will increase. And as you move down the group of your periodic table, your electronegativity decreases. So I actually talked about you moving down the periodic table and your electronegativity would decrease. This arrow is going in the opposite direction. So octet rule, this is when atoms will gain or lose or share electrons in order to have 8 valence electrons in their outer shell. Okay, and having these 8 electrons in their outer shell is called the noble gas configuration because they are then stable themselves. Isoelectric, on the other hand, isoelectric is when an atom and an ion have the same electron configuration. For example, when you have sodium loses that 1 electron, it now has the same number of electrons as neon. This makes neon and sodium isoelectric. The small elements that you have that don't meet the octet rule and just have simply fill up the s2 orbital, well, they follow the duet rule, and keep in mind that's 2 valence electrons, and that's hydrogen and helium. Your pseudo noble gas configuration is transition metals or outermost s and p orbitals are filled, but they do not have the same number of electrons as their nearest noble gas. That's because keep in mind that the transition metals have the d and f electrons are present, okay? Moving on to the general transfer reactivity, metals have a higher activity towards the left side of the periodic table and towards the bottom of the periodic table. Nonmetals, on the other hand, have a higher activity towards the right side of the periodic table and towards the top of the periodic table. Keep in mind that noble gases are always inert and they have no reactivity. The metals, you guys remember, they tend to lose electrons, so they're going to stay on the left-hand side and move down on the bottom. Your nonmetals like to gain those electrons, so they're going to move more towards the nonmetal side of your periodic table. Okay? Well, I hope that this helps you understand periodic trends and using electron configuration. Thank you.